Excuse me.
Yes, good morning.
Good morning. So I have a bit of a problem with logging in because apparently I think somebody else is logged in on my account.
Oh, it's probably me because my number 13 also doesn't work, and I tried 14. I think it's you. Yeah, am I right?
No, I'm actually logged in on number
So
two.
it's me. Okay.
Let me organize this. Give me a second. Just a moment, okay? Okay, please check whether you logged in on your computer number.
Excuse me, my
Yes.
computer number isn't correct because I'm logged in computer number 4, and here on the list I see I am number 5, but to be honest, I don't know Mr. Dominik Kotala. I think he isn't in our group.
Yes, but please let me know who is. So I will check your presence to find out which computers are free. Mr. Hryniewiecki, you are there, yes? All right. All right. Ms. Cantor?
I am present, and also my computer is my login is occupied
All right.
already.
Ms. Konstanty?
I think she's absent and she won't attend our course anymore.
Okay. So let's remove it. Mr. Kotala is here, I think. But do you have problem with? Oh no, he's not in. You mentioned yes. So
Yes, he's absent.
He's absent, but only today, yes?
No, I think he isn't in our group.
No, he never was.
He never was, yes.
He's not studying with us.
Yes, but all right. Ms. Kozub?
Yes, I'm present and I am logged in computer number 4.
Okay. Miss Łyszczarz?
Yes, I'm here and I'm logged in on computer number 5.
You are logged in or not logged in?
Yes, I am. Everything is fine.
You are, okay.
The number of the computer.
Miss Manteris or Mrs.? So not present, I presume. Miss Mendela?
I'm present and I'm logging on computer number 7.
Okay. Mrs. Mojecka?
I'm here and I'm logged in computer number 8.
So 8? Why
Yes.
not? Why not?
8 is on the list.
Yes, but I do not understand.
I log into the same computer each time.
I mean, the list that you are showing you now, it's not that you gave us on the first classes. I mean, in the mail that you sent to us, we have different number, and it's because
you have different numbers?
Yes, it's because
yes.
Dominic Kotala that shouldn't be on this list.
So if I remove him from the list, it means that it is now it is correct list.
I think so, at least for me.
Yes,
So
it's same.
okay, Mr. Myczka, sorry.
Present, and I'm logged in computer number 9. So
Okay.
now it's okay.
All right, Mr. Polaczek.
Present and looked on number 10.
Okay. Mr. Talowski.
Present and logged in, but I logged in onto computer number 15 because that's where I was last time because I had problems with number 11. So number 11 is
Is not working. Okay.
Actually, I don't know. I didn't try it today because I had
Okay.
already.
So this is 15. Mr. Tomkiewicz.
Yes, hello, I'm present and I'm logged in at the computer number 12.
Okay, so your number. And Mr. Zając.
Yeah, I'm logging nowhere because my computer number 13 is probably turned off.
Is probably turned off, yes?
Yes.
So please try to log into number 14, okay?
14 is occupied by Susanna Cantor. She was working there last time, so
Zuzanna Kantor,
Yes.
but she told me that she did not log in. So
Let me explain.
yes.
So in the meantime, when you were checking the list, I decided to log in on number 14 because that's where I was working last week, and I have
and you are successful, yes?
Yes, I am.
Okay, so this is number 14. Okay. All right. So we have.
I'm also
Is that
present,
okay?
and I'm trying
Sorry?
to log in right now. Manteris Sylvia.
Sylvia Manteris, yes. But you are already logged in or not?
Not yet. I'm
Not
trying
yet.
to log in
To
now.
the computer number 6, yes?
Yes, 6.
All right. And please let me know. Mr. Zions is not logged in yet, yes?
Yes, I just need the number I can log in.
Which number are you going to log in?
I mean, I'm waiting for you to give me the number because, as I said, like for 13, that's working.
All right. So in fact, which number is free?
Number 11 should be free if it's started working.
Should be. Yes, please check it. But yes, you can try number 11. But Mr. Hryniewicki is not logged in.
Number 11 doesn't work.
Number 11 doesn't work. What about Mr. Hryniewicki? Yes. What? Yes. Did you try again to log into number 1, computer number 1? Okay, all right. So, Mr. Zions, could you please try to log in? But let me see. Mr. or Mrs. Manteris is not present. Yes. No, she is present. But
I am
yes,
present.
But I would like to check why you are in red here by mistake, I think. But did you manage to log into computer number 6 or not?
Not yet. I have got.
But what is the message when you try to log in?
I've got no message yet. I need more time because I don't have a laptop, and right now I'm trying to log in into my friend's laptop. So
okay.
I had to log him out from his apps to be able to log myself onto the Gmail.
Yes, please let me know, Mr. Hryniewiecki, Miss or Mrs. Constanty, or Miss or Mrs. Manteris. Did you logged in successfully last time during our meeting, or you also for some reason you couldn't log into the computers, to the remote computers? Mr. Hryniewiecki, last time did you successfully log in on your computer? Hello? Yeah, but last time, during our last meeting, not today. All right. Okay. What about Maria Constanty?
She's not studying with us anymore.
Any longer. So probably Mr. Zając, please try to use.
Yeah, I just log in on number 3, so yes, I'm okay.
So who is okay, Mr. Zając?
Mr. Zając, yes.
Okay. All right. So this is number 3. So so we have 2 of us, Mrs. Manteris and Mr. Hryniewiecki, who did not log in on your computers. Okay, you know, I would suggest to try again for some time, and not to wasting time, we will start the lecture now. And after that, in the meantime, you can try to log in, okay? All right. Okay, so. Just a moment. Please remind me where we finished our last lecture. What was that? Did we discuss initial and boundary conditions?
I think so, yes.
So we have derived the equation of mass balance for multi-components first for one component system, after that for multi-component systems, and discussed the initial and boundary conditions, yes?
Yes.
Okay, good. All right. And as far as I remember, we also demonstrated some examples of the application of COMSOL, how we can solve mass balance equations, yes? Am I right? It was also diffusion and diffusion with reactions. So yes. I will start COMSOL now because I would like to go into details with the further examples. I will demonstrate some features of the solution of the mass balance equation and illustrate this using some particular COMSOL examples. Yes, and our last examples were for one-dimensional geometry, and consequently some simplification were present, because in one-dimensional geometry, generally the operators of divergence, of gradients, are very reduced. In fact, the divergence is exactly the same as gradient, because this is partial derivative. In practice, that operators differ quite a lot, because of course divergence, operator of divergence, always acts on the vector, while gradient always acts as to the scalar, like concentration. And also the boundary conditions which were presented last time, we used to say that, for example, this Neumann boundary condition, by some simplification, we say that, for example, the flux is 0.
Excuse me?
Yes?
We can see your screen. What we see is only your camera, not your screen.
Oh, okay. So, thank you. In fact, just to remind you that in case of boundary conditions like different Neumann-like boundary conditions, when we set the flux, in fact, we do not set the flux. We set the normal part of the flux. Because, as you probably remember, each vector can be split into normal perpendicular vector and a vector which is parallel to the surface in this point. And of course, only this part which is perpendicular, which is normal to the surface, can enter or go out from the domain. And when we formulate boundary conditions, we always set this normal part of the flux. So this is why we used to write, I will enlarge this, that we do not provide the flux, we provide the product of flux and normal vector. And according to the definition, this is the number, because we have the scalar product. And scalar product, of course, is the mathematical way how we can get the normal part of the vector, in this case, the flux. And it will be especially important in case of two-dimensional and three-dimensional geometries. This is why, for example, when we start our model in two-dimensional geometry, you will see the difference. But at first, let's go back to our new example. This example is the very simple model of grain boundary diffusion. In fact, as you know, materials are mostly polycrystalline, so they are composed of grains, and there is some, I would say, in simplification, some gaps between those grains, which are called grain boundaries. And those grain boundaries, we know definitely that this region, grain boundary, they have different properties than grains. So this is why when we, for example, model or try to describe transport processes of polycrystalline materials, we have to take into account the microstructure of this material. So also take into account the existence of grain boundaries. And as a model of this, we use such two-dimensional model where the grains, this gray, more gray part is those gray part are grains. So we have 1, 2, 3, and 4 grains, and between them we have smaller rectangulars which will represent a grain boundary. And the process which we are going to model is in fact the experiment how we can determine effective transport in the polycrystalline material. So to do this, we assume at the beginning that there is no element in the system. By element, I mean, for example, something like copper, nickel, whatever, what we put on the surface on the sample, and we will observe how this element will diffuse into this structure composed of grains and grain boundaries, assuming that the properties of those two elements in the structure are different. So the equation will be describing the mass balance equation will be relatively simple because there is nothing else like diffusion. So the mass balance equation neglects drift and neglects reactions. We consider only diffusion here. And what are the constitutive equations for this model? So in the grain, the flux is given by the first Fick law. So because we have two-dimensional geometry, so the flux in the grain is minus d dc over dx, and the second element of the vector j is minus d dc over dy. And the similar situation is in the grain boundary. However, this time the diffusivity in the grain boundary is different. This is denoted here as dGB. And of course, here we have the constitutive equations. And as I said, we assume that at the beginning there is no element inside. It is only on the top, and it will be given by the boundary conditions, where we assume that this concentration is constant, and after some normalization is equals 1. And to the rest of the boundaries, at the rest of the boundaries, we can assume homogeneous Neumann boundary condition, and here we have some data for which this model should be calculated. So diffusivity in the grain, diffusivity in the grain boundary. So you can see that there are 3 orders of magnitude difference between those two diffusivities. We have the thickness of the grain, we have the thickness of the grain boundary, and we have the height of this system here. And now I will show you how we can very quickly and nice to define such project in COMSOL. After I would recommend now just to observe what I'm doing, and after that you will practice by yourself, probably slightly modified project like this. So we usually start from this wizard. So we have this time two-dimensional geometry. We need general form PDE interface. And as you can see, we change U to concentration. And after that, we are interested in time-dependent solutions. So this is the framework of our project. This time we have two-dimensional geometry. This is new according to our last examples. And please remind me, what is the usually first step when we start to create project after wizard?
We create parameters.
Yes, thank you. And diffusivity is 0.01, and this is diffusivity in grains. We have DGB, which is 10, and this is diffusivity in grain boundaries. Probably it's better to write diffusivity like here, because D is the name of the variable. Probably this is better. Diffusivity in grains and diffusivity in grain boundaries. Okay, we have the grain size D, which is equal 1. Not yet, not ready yet. This is grain size in the direction X. Direction X, and we have A, which is 0.1, and this is grain boundary. In the direction X as well, and what we this is H. This is 10. This is
Sorry to interrupt, but on your presentation there was A and D was different. I mean yes. A was 1 yes, and D was 0.
You are right, but this is a mistake here.
Okay, thank you.
Okay, thank you, but thank you for your care and that you are active. Okay, right, and probably the concentration on the top is just 1, and this is top concentration. So we have now all the parameters for our model, and the next step is of course geometry. And as you can see now, we have some extra elements which we can use. Our geometry is based on rectangle. So the grain has height h and width d, and this is our grain, first grain. And now we have to create grain boundary. So one of the possibilities is duplicate. So we can call this that it is grain 1, and the second one will be grain boundary 1. And this grain boundary has width A, and of course we have to change the position because it should start here. So if we do this, it will be D here. So you can see that we have now such element. All right, and what we can do now, we can try to just a moment. We have tried to. Where is our geometry? We have transformation here, and we can create. We can copy this object. And which object? This one and this one. So we will copy those two objects, and the displacement will be A plus D. And how many times it will be? We can change this. Let us check now what will happen. So we have another one. So so probably let me see how we can repeat it. Yes, but this is copy. Can we copy? How do you think? Probably the solution will be like that. That did this 2 times. Let me see whether it works. Okay, it works. Okay, and at the end, we would like to add only grain. So probably let us copy this one. Let us duplicate. And what is the X? 1, 2, 3, 4. So 4 times D plus 1, 2, 3, 4. 4 times A. All right. So this is our geometry. This is the example how we can create 2-dimensional geometry. So we can use this base elements like circle, ellipse, rectangle, square. You can also define some shapes based on Bezier, polygons, interpolation curve, line segments. We can add points. We can also change the geometry using fillet and chamfer. So it is slightly similar to CAD programs. Those instructions are, I think, much more restricted to AutoCAD or other CAD programs. However, quite a lot of different operations can be done, especially that we can also accept of transformation, which can be some, as you can see, mirroring, moving, rotating, and copying. We can also can do some logic operations like intersections, different create unions, and so on. So this is one of the possibility for the relatively simple models like this. For the relatively simple geometry, we can quite efficiently, easily create such geometry using console multiphysics. And here you have it now. Of course, what is the advantage of parameterization of this geometry? So when we change, for example, height from 10 to 5, by one click we obtain different geometry. So this is quite nice, I think, and I would like to just outline why we put some parameters, because parameters are, as the name indicates, we can just modify our project by changing those parameters. And when you, for example, use instead of parameters numbers, so you must then remember to change any number. So this is wasting of time, and definitely it's worth to parameterize geometry, parameterize your model, and all the numbers should be here in parameters. The rest should rely on defined variables in these parameters. Okay, so we have created geometry. Again, let us change the shape. No, it's not changed. Change it to 10 again. All right. And what we can do now, what we should do now, is just to create the proper equations which describe our problem. And first of all, as you can see, program took all the domains, so it means grains, but also boundaries. And of course it is not correct. Why it is not correct? Because the properties of the grain boundary and properties of the grains are different. So we cannot use only one general form PDE to describe the properties of this microstructure here. So how we can handle this? We know that we need two such general form PDE. So what we can do here in general form PDE, right click, and we will add another general form PDE. Okay, so this time in this, let's say, upper general form PDE, we have two different general form PDE. One will be for the grains, another one will be for the grain boundaries. And of course we can just let us call this that it is grain boundaries. Okay, and the first one will be just for grains. Okay. So, of course, here in the selection, I have to choose all the grain boundaries, but it is we can do it differently as well. In the definition here, if we right-click, we can add selections and explicit. And we will define just grain boundaries. And in the domain, we will just select those grain boundaries. And if we go back here to general form PDE, now instead of manually select, we can choose here grain boundaries. It is especially convenient when our geometry is more complicated, so it is composed of a lot of different elements. So we can define them only once in this selection, and after that use in different elements of our project. Going back to our general form PDE, you can see now that when we define the region for grain boundaries, which are just blue marked, in the grains, some of the regions were overwritten and they are just grain boundaries. The remaining elements are just grains. So this is exactly what we wanted. So now we have to specify our mass balance equation and constitutive equations for the flux. So how we can do this? At first, there is no, if this is our equation, there is no sources. So F equals 0. And what is the constitutive equation for the flux? Diffusivity for the grain multiplied by the element of the concentration gradient, the first element. And in the direction y, d multiplied by cy. So here we defined our mass balance equation and constitutive equation for the flux for the grains. Okay, we will do exactly the same with grain boundaries. But this time, of course, sources are always also 0 here. And what is the constitutive flux here? dGB multiplied by Cx and dGB multiplied by Cy. So we have now defined properly our mass balance equations and constitutive equations for the grains and for the grain boundaries. The initial values by default are 0, and in our case, this is exactly what we want. But we have to specify some boundary conditions. So right-click and specify Dirichlet boundary condition. And this will be just on the top. We write it like here, boundary conditions, abbreviation on the top. And we can specify the top here. So how to do this? We can either choose yes, so we have top boundary and the value is C0. All right. So in fact, our model is defined. What else is necessary? Of course, would like to see the mesh. And here we have the mesh. This is the default mesh, which was generated by the program. And now let us start do computations. And probably I will break it for some reasons, because I would like to observe what is the progress with time. And there is such possibility in COMSOL. And in the time dependent, you have something like results while solving. And when you open this, you can put plot, mark plot, and display the default plot. And let us repeat our computations. And now you can see what is the progress in concentration in this materials microstructure. So you can see that color corresponds to the value of the concentration. So red is the highest concentration, 1, and blue is the smallest, 0. And as you can see, mainly transport occurs through the grain boundaries, because the diffusivity is 3 orders of magnitudes higher. In the grains, there is only very small region of diffusion, because of the same reason, that the diffusivity of the grain is much smaller than on the grain boundary. But what you also can see, that there is diffusion not only in the direction Y. There is also diffusion in direction X, which means that some concentration which is increasing in the grain boundary affects concentration in the grain, but from this part, you can see. So we can now extend the time. So let us say that this is for 10 seconds and repeat our calculations, and you will see how nicely it goes. You can see that the diffusion in the grains are still much smaller than in the grain boundary. But now we can simulate the situation that there is diffusion only in the direction Y. There is no diffusion in direction X. How we can change it? Just diffusion in direction 1, so this part is just 0. We multiply by temporarily by 0, and also in grains. And let us repeat our calculations now. You can see that the transport occurs only in this direction, which means that there is no interaction between the grain boundary and grains. So such definition of the problem is like solving each element separately. So grains and diffusion only in the grain, boundary and diffusion only in the boundary, and so on. So there is no interaction between grains and grain boundaries, because we change constitutive equations and assume that transport occurs only in this direction. We can go back to our previous situation, the proper one, and we can again see that this process is related to each other. So the transport in grain boundaries affects diffusion in the grains as well. Okay. Right. Could you switch on your camera, please? Thank you. So, any comments to this project?
Yeah, you were going so fast that I missed something and there's something wrong.
But you wanted to repeat it on your remote computer, yes?
I will try, but I don't know if I can.
Okay, it was. I did not recommend to repeat it together with me. I know that it was fast, but I wanted to show you that it can be really efficiently done, and it is a nice job to do this. And as you could see, I hope that I believe that it was your impression. But in the next step, of course, we will go into details and discuss this topic in details, because this will be your first project in two-dimensional geometry, okay? So don't worry, Agnieszka, it was not necessary to be successful. you are just listen to me, and that's all. Okay, any comments about model, phenomena, COMSOL, whatever? You like it, you hate it, you want to go for a coffee or different activities? Okay. Yeah. So I agree, because for just it will be some comments from my side. I was as a student, I was interested in modeling, and I was doing mainly calculations in one-dimensional geometry, which is frankly speaking not very fascinating story, yes, because everything is going on the interval, yes. So it is really simplification, but what we really know, what is very important in material science, is that the microstructure of the material determine its properties, yes? It's the key point. If we go into smaller scale, we start to talk about nanoscience, yes? When the amount of grains is so big that the properties of the bulk are completely I exaggerated a little bit, not completely, but is also very important according to the properties of the grains. So this is why especially such modeling in two-dimensional geometry is very interesting and very necessary, I would say, because the model like this, which I presented before, is of course very simple geometry. Model is simple, everything is simple, but what is important that we can. How long does it take me? 15 minutes, 10 minutes, something like that, yes? So very shortly you will need the same amount of time to create such simple models. And what is why we do this? Of course, the idea is that we can always make an experiment, but it takes time, it takes money, and it's definitely not necessary to do everything experimentally. So this is why we try to model different microstructures. We can just create our own microstructures and test it. What will happen when we change this parameter in the direction X, in the direction Y, amount of extra phase. And it can be done for any property, in fact, for transport of mass, for transport of heat, so for transport of electricity, optics, mechanical properties. So everything can be or should be tested. So this is why it is very important to have an efficient tool which will allow us to create our imagination. Because in fact, we can expect something when we create, yes, model, when we, what will happen when we add phase about different properties and so on. But in fact, we should definitely confirm this. And one of the first way how we can do this is just modeling. Of course, modeling can't stop experimental verification, because model is always a simplification of the real process. You have to remember about this. And I also remember, which means that modeling is something like a first seed, yes? So we perform different modeling cases. Call this, for example, sensitivity analysis, when we know how particular properties change the behavior of our domain. And after that, when we find some interesting cases, we should definitely make an experiment, perform an experiment, and verify our model, but not for all the cases. Yes. So that's the point. And what we will do, we will spend some time just to play a little bit with this two-dimensional modeling. First of all, create different structures, creating based on different models, and do this sensitivity analysis. So this is what we are going to do for the next 2 meetings. And when we are successful and when we have some practice in this field, we will continue the problem, for example, of energy transport and different aspects of material properties. I would like to ask you, what about logging on those computers? Because 2 persons were not successful. What is the situation now? Of course, but Marcel, you can't log in, yes? Computer 1 is not responding, yes? And what about Maria and Sylvia?
Maria doesn't study with us. She won't be on the classes anymore.
And what about Sylvia? Sylvia, are you there? She's not with us. She is with us. Sylvia, can you hear me?
Yes, of course.
So why don't you answer my question? Did you log into to your computer or not, to the remote computer or not?
Yes, I am. You can see me?
So you are logged in, yes?
Yes, I am.
Computer number 6?
Yes, of course.
So I'm very glad. So the only person is Mr. Hryniewicki, who is not successfully logged in. Am I right? Please use this number 3, okay?
I am on number 3.
All right.
So I need to open the door.
Sorry, Arthur, I can't hear you. Could you repeat, Arthur?
I need to open the door. I'll be right back.
Okay, all right. What do you mean code? But did you receive a license file from them? But could you send me an email which you received from COMSOL? Okay. Okay, so did you put your data for the verification or not? Yes. Yes. And they did not respond, yes? Yes, but I think Marcel, that you should receive from COMSOL an email, and when you receive an email, it will be possible to download and install the software. Okay, I think so. When you filled in this web page, when you contacted them. So usually the answer is 1 business day. So please be patient a little bit, okay? So try again. Try again. Just a moment. Let me be allowed to go to COMSOL web page. Yes. And there is something like where is this contact COMSOL? We can just there is some contact there. Contact COMSOL, yes. Did you use this form? All right. You are interested in COMSOL? Okay. All right. So please wait 1-2 days. If not, please, because you have also here info console.com. You can also just write an ordinary mail to them, not using this form, that you would like to check the software, and you are asking for the I would say demo version of the program, or just to find out how it works and so on, that you are interested in. You can after our classes or during, when you have time, you can just write an email using this email address as a parallel way how to get the software. Okay. Yeah, but did you try to log into computer number 3? Patrick?
Yep. Yes.
So why I have number? Oh, sorry. Not yes. Yeah. Oh, whoa.
Number 11, you could try it again if it's working
but
now.
Number 11 were not working. Yes, was not working. So, but please try to use number 13. Okay, because Patrick is using number 3, but probably number 13 was released. Try number 13, 13.
I think the main problem with those computers is that they're not on, they're not online, not that somebody else is using them.
But computer number 11 is definitely not online. But number 13...
Number 13 too, I tried it at the beginning because this is what I first computer I tried to log in.
But it was in gray?
No, I cannot choose when you are opening the remote desktop. Okay. I couldn't even choose number 14.
I understand. Which computer? All right. Could you share your screen, please? Mm-hmm.